We have a lot to cover in the next several lectures, so I'll try to I'll be using some slides here and again just to make things a little bit more palatable and nicer for everyone. I think that by now we all have the necessary background to understand the basics of machine learning and pattern recognition, and hopefully we can move a little bit faster from now on, okay? So remember that we have this model of machine learning, right? Where we have an input variable x, so this is our input, and we have a functional mapping of x onto some other variable y, right? So this functional mapping usually goes from the real domain or some other domain, the complex domain, what have you, of p dimensions, maybe to the real domain of q dimensions. And that is what allows us to do what we call learn that function with the methods that we have derived to actually do the mapping from our input to our desirable output, right? And the way that we've been doing this until now, or one of the methods that we have seen but extensively, is by trying to model this using a probabilistic approach, in which case x, our input, is assumed to be drawn from some distribution, right? Some probability density function. And this probability density function is assumed to be given by a certain number of parameters, right? And we have seen the normal model, Gaussians. We have seen super Gaussians, sub-Gaussians, mixture of Gaussians, mixture of t distributions, mixture of any type of distributions that you can think of, right? All these are parametric models. That allows us to understand the underlying distribution of the data. Now remember, if this is RP, our simple feature vectors, right, are drawn from this underlying feature space. I'm sorry, for this feature space, then in that feature space, the underlying distribution may be, who knows, something like this, right? And if we could estimate this underlying distribution, and then we get a new sample, let's do this. If we have a new sample here, right, and we know that this is very unlikely to be drawn from that underlying distribution versus this one, which is certainly much more likely to be drawn from that underlying distribution, then one does belong to that distribution and the other one doesn't, right? So for classification purposes that we have been discussing, that would mean that this belongs to the category or class defined by this underlying distribution. This one may not, or at least this one belongs to this distribution with a much higher probability than this one, right? Great. So that is the most common way to estimate the underlying distributions. The easiest way, obviously, is to assume that the distribution is a normal distribution. You just need to compute the first moments and the second moments of the data, the mean and the covariance matrix. Easy as pie. It goes very quickly. It works very well, except that the underlying distribution is unlikely to be normal. So we have seen other distributions, and most useful is the mixture of normal distributions or mixture of other distributions, right? In which case you need to estimate not only the first moment, second moments, maybe more moments if you're using super Gaussians of the data, but you also need to estimate how many models do I have in my distribution, what are the different moments of each of the models in my mixture model, and so on, right? So it gets slightly more complicated. The computations are trickier. There is no MLE, right? There is no maximum likelihood estimator that we can use to, like, there is an MLE for the mean and the covariance matrix that we derived, there's no MLE for the mixture models, right? And we derive a specific algorithm to solve that problem called the EM algorithm, right? That allows us to find a reasonable result most of the time. So another way to address this problem is to use what's called non-parametric models. And by non-parametric, we mean that now everything here stays the same, but now this probability density is not given by a set of parameters, but rather is estimated without the need of estimating these parameters or defining these parameters. So let's see how we can do that. So if I need to estimate, remember that distribution, this is the probability, right? So this is the probability P of a vector x, right? And let's say that I want to compute that probability of that vector x to be in a region, in a given region R, okay? Now, this, as you know, if you knew the density, right? This is the density right here. If we knew the density, then we could compute the, we could integrate over that region R, right? The density over differential of x, right? Easy. That's my probability, capital P. I can also write this down as my density here times the volume, and the volume is given by this integration, right? When I integrate, what's integration? It's nothing else than computing the volume under the curve, right, of the distribution. So that I could write it like this. It's the same thing. So now, suppose that you have n samples, okay? And let's assume for discussion, the sake of discussion, that they are IID, as we have done before, and that these n samples are drawn according to our distribution, right? Our samples are always drawn from the underlying but unknown distribution, right? That's why we can estimate the underlying distribution, because our samples are drawn from that distribution. Then what we can do is we can write the probability, right, that we had before, but we can write it as follows. We can write the probability that this belongs to that distribution, or that what have you, right, to the power of k, where k is the times that this sample, right, represents this specific value or this specific category, if you will, of the density or the whatever you are trying to represent, right? And if k instances of the n samples that you have, if k are represented by this probability, right, the other n minus k are represented by 1 minus that probability, right? I mean, duh. So you get this binomial distribution here given by this, and from this, you can compute the density, which is nothing else than the density is going to be the number of samples given in that region that you're interested in, R, right, divided by n. It shouldn't be a surprising result, right? K over n, obviously, right? If 10 of my 100 samples are in that region, then it's 0.1, yeah, given. Normalized by the volume of that region, right? Because you want to compute the density, you want to normalize by the volume. Because remember, the integration of the density has to be equal to 1, right? So the volume has to be considered. So here's an example. Let's consider that P is equal to 0.7, right? So if I only have 20 samples, then I'm going to get K over N, probably a very relatively large number like this, right? You're going to get the distribution of, or an estimate of the distribution like this. But as the number of samples increases, you're going to get the thinner and thinner and thinner estimate. And as the number of samples and the area R decreases, you're going to get more and more accurate results up to the point where you get a delta. So let's see how this works. If to do this estimate here that I have right here, right, what do I want? I want R to be sufficiently large, right, my region to be sufficiently large, such that I include a certain number k of samples in that region, right? If I make the region too small, then it will not include any samples, right? That's not too good. So R needs to be large. But if R is too large, then we're basically computing an average, right? Which is computing an average over the whole space or over a very large area of the space. And that's not what we want. We want the actual density at every single point. So R, if possible, should be small. If R is small, then that means the same equivalent that V needs to be small, right? Now, if V is too small, then that region will include 0 samples, right? And then you are going to be unable to estimate the density at that point. OK, so how do you solve this? You want R to be large. You want R to be small. There are 2 methods to solve this. So let's go with the first one, Parzen windows. With Parzen windows, let's work like this. And we're going to do Parzen windows first to get to k nearest neighbors, which is the method that we want. Now, k nearest neighbors, it's the simplest algorithm that you're ever, or one of the simplest that you're going to see in this class. But it's usually one of the most misunderstood algorithms. People say, oh, just k nearest neighbor. Yeah, it's obvious, right? Yeah, but where's the math behind it, right? Why is such a good method? And when we get to studying classifiers, we'll actually show that k nearest neighbor is one of the best classifiers you can ever get. OK, we'll get to that in a later lecture. So to define Parzen windows, let's define h sub n as the length of the edge of a d-dimensional hypercube that defines Rn, right? So our region, right? We're going to define our region as a cube, any more dimension a hypercube, right? And all the edges of that hypercube are going to be the same. The length is going to be h sub n, okay? That means that we could compute the volume as hn to the power of p or d here, the same thing. And then we're going to define that window as follows. For a vector u, okay, I'm going to have 1 as the output of this function if uj is smaller or equal than, here's 1/2 because I'm assuming that this hypercube is centered at 0 and has length 1. Okay? If not, it would be hn over 2, right? Same thing. Okay? All right. And 0 otherwise. So this is a function that only tells me whether a sample, a given sample, is in that region or is not in that region. Okay? All right. Now, we can use this now to define to determine when a vector x is in a region by simply subtracting this. I'm not sure. OK, anyways, getting this this region. So here note, OK, yeah, let me go back. So here I have the unit hypercube, right? And here what I'm doing is I'm dividing by the length of the hypercube, right? Which is equivalent because now I'm converting this into a unique hypercube, right? And I want to know whether the distance from my sample to the mean, right, is actually within that hypercube, right? And again, that's going to be 1 if I'm in the region and 0 if I'm not. And that allows me to define now this neo function here, which is nothing else than the addition of all the samples that I have, right? So if I end up with k samples in that region, this is going to be equal to k, right? So far, so good? All right, excellent. So the density is now given, right? The density that I want to estimate, my p of x, is given by this function that just computes the number of elements in that cube, right? K over n, divided by Vn, right? Which is the volume, right? And it just represents the Vn because Vn is the volume that you compute with that n that you have. Now, since we want Pn to be a density function, we need to impose two things. First, that this function is positive or 0. And second, remember that this function, when I integrate this function, the volume is equal to 1. Right? These are my requirements to make this a density. So to do that, let's study what happens. We can define this function, this new function here, delta of x, which is my function centered at the mean, right, of that window, divided by the length of that window, okay, over the volume. Now, if I apply this function by inputting this value here, right, whether that sample is in the window or not, then I get exactly the same thing I had before, right? I get now the estimate of the density. So think about this. This is the volume given by the length of the hypercube. Now, if that hypercube is of length 1, you're going to get this estimate for a certain number of points, right? You're going to get an estimate like this. Why? Because the hypercube is really large, and you're getting an average of the number of points, right? As you keep getting that window, making that window smaller and smaller, then you're going to get more of a peaky distribution like this for that center point, right? I'm only concerned about the center point. And then the smaller that I make it, say 0.2, I'm going to make it even more to that area, right? So these sample vectors that I have in that point are not going to have an effect on the other regions nearby, right? Okay. Now, the value of Pn depends on x1, x2, xn, my samples, right? The samples that I'm given, right? I need to estimate the underlying distribution from my samples, right? Okay. Let's compute the mean. The mean of Pn, let's call it Pn bar. We shall say that Pn of x converges to P of x, which is a true one, right? This is the true one, and this is my estimate with n samples. If the value converges when the number of samples increases to infinity, and if the variance goes to 0, okay? That means that when I increase the number of samples to infinity, that average that I obtained here is identical to the true underlying distribution. But it also has to be the case that the variance that I compute between different estimates, right, has to be equal to 0, right? Okay, so the mean has to be the same as the true one, but the variance has to be 0. Let's see what happens when we do that. Let's start with the easy one. That's a simple one. Convergence to the mean. So what's the expected value of the convergence to the mean? So this is the expected value of P of n of x, right? And again, we're assuming that the xi's are IID, as we said. And we know that this function, we have already computed this. This is x minus v, or the center or the area that defines my window, divided by the size of that hypercube, divided by the volume, right? Okay, this is what we have computed already, right? So I haven't done anything new here. And now what is to compute that expected value? If I have an infinite number of samples, I just integrate over the whole area, which is this equation right here, right? This is to compute the expected value. True? Okay. And this, remember, I can rewrite it like this with this delta function here. And now I have here a convolution, right, that defines PV, right, with these delta functions. And if I make this delta function, remember, let me go back, this delta function here, right, this delta function we have defined, gets smaller and smaller and smaller as I make this hypercube smaller, right? If I make this close to 0, the size, then I get the delta, Dirac delta, right? Then in that case, right, if this is just a delta, what am I doing? I'm just integrating PV dV times the delta at each position in my space. And what's this equal to? This is equal to the density I'm looking for, right? So if I have an infinite number of samples, then making the volume of that region tend to 0 actually gives me the value that I want to, right? The expected density. So I already know how to solve the problem. All I need is an infinite number of samples, okay, a very large number of samples. And I need to make that region as small as possible. And I know that this method is going to give me the same result as the estimate of the true underlying distribution. Okay, so now let's see what happens to the variance. To compute the variance, again, the variance is nothing else than the expected value of this term right here, right, which is the variance that we have derived and used before, right? And here, note that I have my element that I had before minus the corresponding mean, right? A square. That's the equation of the variance, right? So I can compute the expected value of this. If you rearrange terms, you can write this like this because this does not depend on this expected value. So you can put this out, the squared, and so on. And then you integrate. So let's integrate here. Let's see. We're going to have this function squared right here, which if we make this delta smaller and smaller, remember, then this PV would be equal to the actual true distribution, right? That's what we have seen by with the result of estimating or converging to the mean. Okay. But this is what we're going to write instead, because this is the maximum of this function that I have here, right? This function here, times what's this? This is nothing else than the mean, right? Here, this is the mean right here that I can get minus the mean. So this is the mean right here times this function that I have right here divided by this normalizing term, right? And see how this works? Okay. So now that I have this is a bound. This is not the actual number, but this is the upper bound of this number, okay, that I have here. And what happens when I look at this? Let's check this out. To obtain a small variance, remember this variance ideally should be equal to what? 0, right? So to get this small variance here, to get this as close to 0 as possible, how are we going to make this equal to 0? To obtain a small variance, we want to have a Vn that is large, right? Because to make this 0, I can only make this 0 if this volume is infinite, right? You see that? Okay. Now, again, we need a small value of the mean and a large a small value of the mean. We need a small value of Vn to compute the convergence of the mean, and a large value of Vn to compute the variance. So what's going to give? The only solution to this problem is the following. You have a very large number of samples, n, so n has to tend to infinity. We make Vn tend to 0, provided that n times Vn tends to infinity. Now, if that's the case, then this is still infinity, right? And this is still, where am I? Here. This is still 0, okay? Which allows me to get this equality. So, for example, these are just examples. You can make Vn equals to these equations that I have shown here. Okay? You see how this goes? Now, obviously, we'll get to that. In practice, you cannot make this go to 0 and this go to infinity unless you have a tremendously large number of samples, right? And We're in the area of big data, but data ain't that big. I can tell you that. It's large, but not that large, right? So to see how this would work in theory, let's see an example with Gaussian densities. Okay, so let's say that this function that I have defined before, it's equal to a Gaussian, right? Instead of a hypercube, so that it's easier to compute. So if I do that and I generate a certain number of random samples in that two-dimensional space, and I make h equal to 2, right? And I just have one sample, then I'm going to estimate this. If I increase the number of samples, I'm going to estimate this. Increase the number of samples, I'm going to estimate this density. And if I had an infinite number of samples, this is what I'm going to get, which is my Gaussian. And what do I get a Gaussian? Well, that's what I have right here, right? Okay. If I decrease the size of my window, then what do I get here? Well, I get a small Gaussian, right? The size of, or the type of window that I have, just about the position where I have generated one sample, right? If I generate 10 samples, then I get 10 small Gaussians, right? In their corresponding location. If I have 100, then I have 100 peaky Gaussians, right? And so on. But at the end, if I really had n samples, infinite samples, it doesn't matter what size my window is, I will always converge, right? This is what classification based on Parzen windows should look like. You have here black dots and red dots, right? And if you use a small window, you're going to get this density for the blacks and that other density in white for the reds, right? So now if I have another test sample, let's say here, I'm going to say it belongs to the red class because that's what these densities are telling me. But if I make the window larger, these are the densities that I'm going to estimate, right? All right, so how are we going to go about determining that size of the window, right? I mean, the ideal solution, we know what it is. Make the window really, really, really small, and then the number of samples infinite. But because generally you're not going to have an infinite number of samples, we have to find another way. And this is where k-nearest neighbor really comes in. So the solution that k-nearest neighbors proposes is why it's to think back about the why we have this problem to begin with. We have this problem of the window size because if we remember the window too small, then it does not include any samples. But if we make the window too large, then you're just computing an average over the feature space, right? So how can you go about it? What you can do is to change the size of the window depending on which region of the feature space you are at. If you are at a region where the density is very small, you want a larger window. And if you're in a region that is very dense, you want a smaller window. So how to determine this? K-nearest neighbor says for each position that you're going to estimate your density, start with a tiny, tiny area and keep growing that area until you have k samples in that region. Okay. Now, you center the window at, once you have done this, you center that window at, say, a testing sample, right? So you have your training data can be very large. And now you get a testing feature point, right? So let me go back here. We have, say, these simple feature vectors that represent one class. And let's say, I don't know, cars, right? And these other samples here that represent bikes, okay? And now you get a new test sample, and your test sample, say, it's right here, okay? And what do? What you do is you start with a window around your test sample, and you keep growing that window until it includes a certain number of samples, right? Generally, you want an odd number of samples. So let's say that we grow like this, and we include these 5 samples right here. Okay. Now, what do you do? Okay. So the density in that point, right, that point centered at the test sample, is going to be given for each of the 2 densities that you might have here. So we have blue and black. So we're going to end up with 2 densities, right? The density for blue is going to be 3. Oops, I included too many, didn't I? All right, there you go. It's going to be given by 3 samples of 5, right? So the density of blue is going to be the probability of x is going to be 3 over 5 divided by the volume of that region, right? Correct? And for the black class, I'm going to have the density is going to be 2 over 5 divided by the volume, right? Correct? So this is how you can compute this. Now, it can be shown, as we have done before, that as the number of samples tends to infinity, then obviously k tends to infinity, but then still this tends to 0, which is what you need to guarantee the convergence to the true distribution that we discussed before. And these are therefore necessary and sufficient conditions for Pn to converge to P. Okay, we've seen that. In practice, here's an example, for example, of how to estimate densities with different numbers of k's. 2-dimensional case, this is the density that you estimate given this 2-dimensional space and these random points here, sample vectors, and so on. You have a certain number of examples that I've posted in the slides. Now, with that, you can do a variety of things, right? One of them is to compute the posterior probability. Why do you ever want to compute the posterior probability? Well, remember that the posterior probability is what's going to allow you to do classification, right? Because until now, we're just estimating the density. But what I really want to get is what's the posterior for my test sample red here, right? OK. So how are we going to do that? We're going to compute, right, the probability that I have here, the probability of x for each class, say class Wi. Okay? This specifies one class. And that is given by the number of samples I have in my region, right, for that class, divided by n, divided by the volume, right? So the posterior probability is going to be equal to this, applying Bayes, as we have done before. There's nothing new. So the probability of my class I, given my samples, is given by this value here, divided by this value, which is nothing else than ki divided by k. That means that the posterior probability, let's go back here, the posterior probability for, let's call it the posterior probability, well, let me just do here for I, the black class, okay, of my sample x, it's going to be equal to, let's see, I have 5 samples and 2 are black, so 2 over 5, okay? Whereas the posterior probability, let's call it j, for the blues are going to be 3 over 5, correct? Okay. And now applying Bayes again, you know, the likelihood ratio, which class is more likely, the black one or the blue one? The blue, right? So you're going to say that this sample vector is most likely to belong to this class, right, the blue class. Why? Because the density is larger for the blue than the black, right? And that goes back to what we had at the beginning when we were talking about Bayes. Remember that we had the red class, we had the blue class, right? And when we were at a certain position, say here, right? At this point, this is my testing, would say, this is the density of the blue, this is the density of the black, this density of the black is larger, therefore I'm going to consider any point, any simple vector in this position of the feature space to belong to the black class, right? And this is exactly the same. You're computing the densities non-parametrically now, but you're saying, well, the density in that region is larger for the blue than for the black, and therefore you're going to consider that the black class. Now, at the end of the day, this should sound like super obvious, right? And that's where people get lost by saying the neighbor by the same, but this is just a trivial part. Yeah, it is. Because all you do is, at the end of the day, of the k-samples that you include, remember, you grow the area until you have k-samples, right? And of the k-samples, you say, okay, which is the class that has the largest number of samples of the k? And you go with that. Yeah, but there is actually a reason why this makes sense. It actually is the base solution given by this. Okay. So again, how do you do that? This is a very simple algorithm. Every time that you have a simple vector x, you grow the region around x. It could be a hypercube, it could be a hypersphere, it could be whatever region you want to do. Usually people use a hypersphere because that corresponds to n1. Hypersphere corresponds to. You see, people saying that k-means neighbor is simple, it's easy, but not absolutely easy. Why do people usually use a hypersphere instead of a hypercube? What's the difference? Because a hypersphere corresponds to a very specific metric, the L2 right? When I grow a hypersphere, I'm considering that all the points in the surface of that hypersphere have the same distance from the testing sample. So I grow until I include two samples. If I use a hypercube, what am I computing? The L1 number, right? And so on. You could use any other norm that you want, right? But that's a selection of the metric in the k-unit neighbor. Depending on the metric that you're going to use, then the metric should be specifically designed according to your problem, right? Depending on the metric you use, you are going to represent your region with a different type of shape, of structure. So you grow until you include k-samples, and then you compute your posteriors, and then you just use the largest posterior to the recognition. So this would be nothing else than doing the argument that maximizes this posterior probability, right? Pn of wi x, right? And I want I, correct? Okay, now there are many possible k-nearest neighbors depending on the k that you want to select. But there's one that is obvious, right? What happens if k is equal to 1? Then we call this the nearest neighbor rule or classifier. And this is a very simple, very pretty much a terrible algorithm that you could design, but it's a straightforward algorithm to design, right? This is how it works. You have your feature space here, right? You have your samples that are given to you, your labeled samples. You get a test sample, then you compute the distance from that test sample to your training samples, and you find the closest one according to your metric, right? You have to define some norm, norm 1, norm 2, what have you, right? And then once you have a norm established, you find the closest sample. And if, say, this is the closest sample, you say, okay, my test sample belongs to the same class as the closest sample, right? makes intuitive sense. And you may be wondering whether this is a good algorithm or not. And if you're wondering this, it's a good thing to wonder, because this can be implemented in, again, 2-3 lines of code. So, I mean, if that's a good algorithm, why not use it? Well, it turns out this is actually a pretty good algorithm. And it can be shown that the error, the classification error of this algorithm is bounded by twice the base error. Now, yeah, twice the base error, it's pretty large, but it's not too bad, right? I mean, compared to the difficulty of computing the base classifier, which we know cannot even be computed in most cases, this is straightforward, and at max, you may get better than this, but at max, you get twice the base error. So let's see why. Let's see how we can do that. So let's assume that the number of simples is very, 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 very large, right? Then x, it's obviously your test sample, is going to be close to its nearest neighbor. Let's call the nearest neighbor to your sample x and n, okay? This is the nearest neighbor of my sample x. And what that means is that the posterior probability of my sample is going to be extremely close to the posterior probability of its nearest neighbor, right? I mean, obviously, if they are really close in the space, then the density, unless there is something really weird about the density at that location, overall, in general, right, it's going to be very similar. Okay. So let's consider what happens when we use the nearest neighbor approach in our feature space. And what happens is that we divide the feature space into areas, right? We can do a tessellation, if you will, of the space into a small different areas, like this one shown here in 2D. This is like in 3D. It looks really bad. But this one in 2D, basically, for each sample, say that we use the true norm, then what this tessellation says is that if I have a sample, a test sample in that region, this is going to be its closest neighbor, okay? But if I have a sample right here on the other side of that line, this is going to become its closest neighbor, and so on, right? So you're basically dividing your region into this, or you're creating this tessellation here, and then because these are the red points, this is the density now of the red points, and this is the density of the black points, right? So this is basically what this means, that the nearest neighbor rule will divide this into or will create these cells, this tessellation of the space. So what happens here, yeah, let's go back to this, is that the probability of the error, right, in general is going to be 1 minus 1 over c. Okay, let's see that. All right, the base, remember, the base classifier minimizes the probability of the error, right? This is the best, the base optimal classifier means that it minimizes the base error that we know is the smallest error we can ever have, given the densities, right? Okay. So what is the probability of the error given my sample x? We can compute that probability of the error as 1 minus the probability of my posterior, right? And remember, that's what we used to do here, right? When I have a test sample here, I'm going to say, okay, this sample belongs to this class, except that sometimes, according to that density, it's going to belong to this other class. But I'm better off by saying it's a black class, because I'm going to make less mistakes than if I say it's a blue class. But obviously I'm going to make mistakes. Sometimes it is going to be the blue class, because there is density, right? Some points will belong to the blue class. So that's the same thing here. That's what this represents, right? Which can be written like this, which is a probability of my error given the density, right? Okay. Now we want to prove this. This is a little this is a tighter bound than the one I mentioned. Usually you will see the 2p bound, okay, where p is the base error, okay. This, as you can see, it's 2 times p minus this other term right here, right? P times this term. So you have c over c minus 1, c number of classes that you have, and p square, the base error, right? So it's actually even better than 2 times p, but let's, for the sake of simplicity, you can assume that it's 2 times p. All right. So I'm just going to give you the basic equations, and you have in the handouts and in the books all the derivations if you are interested in this. But let's go through those very quickly. So you can show that the probability of this, right? This is the probability of error that we had. Remember, this is nothing else than the probability, the base error that we have defined here. But now this one is defined by given the n number of samples that I have. Okay, so I have n samples, and I'm going to say that n tends to infinity, meaning I have a very, very, very large number of samples. Then this is, of course, equal, as we have said, to 1 minus the posterior probabilities, right? And since this is approximately this other thing right here, and we have already established this, if we integrate over x, my yields, slides are terrible, yields 2 times p, okay, if you integrate this term, okay? So this is the bound I really want you to remember, that the probability of error of the nearest neighbor is smaller or equal than 2 times the base error. Now, we also know that this posterior has to be 0 or positive. We also know that the sum of all the other posteriors that do not belong to that class I, right, are equal to 1 minus this, right? And that this, obviously, is our base error. That's the error that we are making, that we're adding, right? This error right here. That's the error that we are adding to our classifier. And therefore, we want to minimize this. And now, okay, so what you want to do is to make these probabilities identical. So let's see how this works. The posterior probability for class I, it's equal to this term right here if I is different than m. Remember, m I'm considering for all the possible other classes right here, right? And it's going to be 1 minus p, the probability of the base, or the base error rather, excuse me, which is this one right here, right? Which is given by when I it's equal to m, okay? And then if you put everything together, you're going to end up with that term right here. And if you just expand it out, you're going to see that this is equal to this term right here, okay? All right. Now, if you remember this, great, but certainly remember that, okay? 2 times the base error. So here's what's happening. If this is the base error shown here for a classifier, and this is your actual error for your classifier, right? The base error, it's obviously a line that goes diagonal, right? So it's a function. If this, let's call this x and this y, f of x equals y, then it would be x equals y, right? It's a unitary function, right? It makes an assignment of x equals to y, because if you're using the base classifier, the probability of error is the base error. Now, if I'm using the nearest neighbor classifier, then this is my error. This is the line of my error, which is 2 times the probability, 2 times the base error, right? But what happens with this? Okay, what happens with the k nearest neighbor? The k nearest neighbor, remember, grows the area until you include k samples instead. This is the same as we have shown before, as the posterior probability is going to be the posterior probability for m to the power of I. I is the number of times that I observe that, times the times I do not observe that distribution, right, or that class, 1 minus the posterior, right? Now, if you do all the derivations again, you end up with this term right here for the probability of error. And this is the function of the probability of error for, again, this last one here, this line here that you have straight line, right? This is the base error. And these ones, these curves, are the k nearest neighbor. And note that as k increases, then that curve gets closer and closer and closer to the base error. So if you can make k equal to infinity, which means that you have to have a very, very large infinite number of samples, right? Then the k nearest neighbor is the base classifier. And we know that because we've already shown that if you have an infinite number of samples, and the number of samples multiplied by the volume tends to infinity at the same time that the volume of your region tends to 0, then your density estimation of the k nearest neighbor is equal or approximately equal to the true underlying density. And what does this mean? That when applied the posterior probability using the base equations, base classifier, I get the base classifier, right? I mean, that shouldn't be as a shock. But what it tells you is that even with a reasonable number of k's in your region, right, you're going to get very good results for a very simple classifier like this. Now, why don't we use the k nearest neighbor classifier then? Well, there are several problems. First problem is you need to know the metric, right? If you don't know the metric, we're stuck, right? So the metric, as always, will be defined by your problem, and depending on the problem that you have, you're going to come up with one metric or another. The second problem is computational cost. What do I keep saying? That for the k nearest neighbor to actually work, you need n, the number of total samples, to be extremely large, right? Because you need to be able to estimate the density locally at every point in your feature space, or at least every point that you're going to visit with test samples, right? So n has to be very large. But to find the k nearest neighbors, right, you have to keep growing, which means that you have to keep computing distances, right, with your metric. And this is computationally expensive. This is very computationally expensive, right? So one solution to that is to just compute the distance, say that you're using the Euclidean distance shown here, just using the dimensions of the space, the R dimensions that have the maximum variance, which is given by PCA, right? So you can use PCA to simplify the number of computations that you need to run. That's a possible solution. There are many solutions like that using all the methods that we have already discussed, right? Metrics, again, these are definitions of the metrics. I'll just leave it at that. These are the different shapes, right, that you're going to have if you use L1 norm, L2 for infinity, and so on. You can also use these ideas that we've discussed here briefly to extend pretty much all the methods that we have defined to date. Okay? Most interestingly, I think, is discriminant analysis. Remember linear discriminant analysis and subclass discriminant analysis and heteroscedastic discriminant analysis and all those that we defined in detail? Well, there's another extension of that that's called non-parametric discriminant analysis that uses the k nearest neighbor to estimate the density instead of assuming that they are homoscedastic Gaussian or heteroscedastic Gaussians or a mixture of Gaussians in SDA, right, in subclass discriminant analysis. So it's just, there are many algorithms, as always, to define a non-parametric extension of DA. Remember that in discriminant analysis, we're working with this equation right here, right? And then what you want now is to define a new between classes scatter-matrix that is non-parametric, right? So one solution, for example, to do this estimation is by considering for the samples of each class the nearest neighbors of the samples of the second class, okay? And then compute the between class scatter matrix of class 1 and the between class scatter matrix of class 2 and compute the average of these two. This is one possible solution. This is an illustration of how this would work. For this sample of class 1, this would be the closest nearest neighbor of class 2 and so on, right? I'm just going to skip the details, but you have them in the slides on how to compute this with the covariance matrices and the means of each of the classes. And then what it shows is that at the end, you end up with the same eigenvalue decomposition equation that we had before, because this is still maximizing the trace of SW inverse times SB or sigma X inverse SB, right? You want to certainly normalize these things when you do that. Remember, this is important because you need to make these actual densities. And here's the algorithm that I have included with the eigenvalue decomposition. And this is just a result with some data that is drawn from some really complex distributions, just showing that non-parametric methods work slightly better than estimating the underlying densities with parametric models. This is another algorithm that uses non-parametric estimation. Just to let you know that these are the marginal probabilities. Just there are different ways of estimating these densities. And this one you can, this is the likelihood ratio that we have defined before for our classifiers when we define the classifiers. And you can solve the equations in that way as well. And that's a result for the log likelihood. So I'm going to skip, but you have all these in the slides and the handouts. And you can compute the partial derivative to find the solution of the maximum or the minimum that you want to compute. This is to use the gradient and the Hessian matrix as we have shown for nonlinear least squares, right, estimation. And here are some data results. This will be the LDA result. This is the actual data. And this is what this NDA method, this non-parametric discriminant analysis method, will get you, which is very close to the real underlying data distribution, which LDA would be unable to do. SDA, obviously, subclass discriminant analysis would also be able to give you that. But anyways. All right. Any questions? Yeah, question.
What happens if you have equal priors between classes but a different number of samples from each class?
Oh, that's a very good question. You mean for the k nearest neighbor?
Yeah.
Right. So the question is, what happens if I have unequal priors?
Or equal priors and an unequal number of samples. So you have more samples for one class, but you
unbalanced data.
Yeah.
This is a topic that we'll cover later in the course. Yeah. So, but that's a very good question. Can someone get the lights, please? These are things to keep in mind that we have not discussed yet, but we will have to at some point, which is what happens when the number of samples, labeled samples that I am given, right, for class 1 is different than the number of samples for class 2 and class 3 and class 4 and so on, right? And that we call imbalanced, or the data is not balanced, right? And that can create a whole number of issues, okay? So one easy solution is to do what's called downsampling. This is very typical, which what you do is you downsample to the class that has the smallest number of samples, right? So if I have n1 samples for class 1 and ni for the ith class, and then you select the smallest ni, and then you randomly draw ni samples from the other classes. Now, because you have so if I have, okay, so let's say n1 through nc, and then I find the minimum of ni, let's call it n, I don't know, prime, okay? And then what I'll do is I will draw n prime samples from each class. Okay. But because ni it's always larger, whoops, it's always larger or equal than n prime, right? Then I can repeat this process multiple times, right? So let's say that I want to estimate the underlying distribution of my data for this class. I can do that multiple times by keep drawing ni samples n prime samples each time, right? And once I do this, then I can compute the mean of all these distributions, underlying distributions. I can compute how well I am doing for estimating these underlying distributions, so on, right? So there are many methods that can be used to address this issue. Other questions? Question?
On k-nearest neighborhood method, one figure shows if we increase k, the error will be closer and closer to the Bayesian error. But I'm considering a case where there are n samples, and I choose k equal to n, and then for every point you will get
that. No, that's only true if, remember, n tends to infinity, right? And you have to guarantee that n times the volume, right, of your area tends to infinity, and the volume of your area tends to 0. So the number of samples has to grow faster than the size of, or the reduction in size of your area.
So in practice, how would you say?
In practice, time permitting, we'll get to that. There is a really good paper I hope to cover that explains how to actually, why the k-nearest neighbor and algorithms like this are so powerful. But in practice, if you don't have a lot of data and all this knowledge, you just select a number, right? Odd number, because, or at least odd in the two-class problem for sure, right? You don't want to end up with an even number of samples for two classes. But we'll get to that. Other questions? These are very good questions. That means that you're already asking questions that we need to cover, right? You're starting to understand what happens with all these models. And when we cover this that I just mentioned, we will talk about the theorem that I've already alluded to, which is called the no free lines theorem, that says that unless you have underlying knowledge, anything that you do is irrelevant, because no classifier is better than any other classifier. Right. Yes, question?
Does a feature space dimensionality affect?
Yes. Yes, absolutely. That's what we will cover too in that lecture. So P has to be, N has to be ideally much, much larger than P. Okay? Now, what does it mean this in practice? A good rule of thumb, but obviously that's not perfect, but a good rule of thumb is that N should be proportional or equal or larger, let's say larger or equal than 10 times the number of dimensions. That's a good rule of thumb, okay? Now, obviously, if you're doing genomic analysis, right, and you have, I don't know how many SNPs you can include in genomic analysis, but, you know, millions potential. If you take pictures with cameras these days, and you have 10 million, 20 million pixels, that means you may end up with 20 million dimensions, right? You're not going to get 120 or 200 million samples, right? So what gives? PCA gives and methods like that, right? And that's why these methods are so important. Most importantly, I would even say PCA obviously it's the number one, but second is factor analysis, right? You want to know if there is an underlying model of your data that is given by specific features, then those are the features that you really want to model, right? And then remember that we are talking about our observation vector x. It's equal to some underlying, what we call the latent variable z, right? That is multiplied by a mixing matrix A, maybe plus some noise term, right? Let's call it n. No, n, I already have this. Okay, epsilon's fine. Okay? So obviously, that is the space most of the time that you're interested in, right? And we'll keep coming back to this. We have already come back to this many times, right? When we talk about factor analysis at the very beginning of the course, then when we talk about mixture models, we came back to this, right? And when we were talking about graphical models, we came back to this. And when we talked about some types of deep networks, we'll get back to this as well, right? I mean, obviously, this is super important, right? But then we're getting into other questions like what's the dimensionality of this latent space and so on and so forth. We'll address that. And the question is research. This is still being discussed in research, right? There's no good answer to that. And that has to be related to two things, right? The dimensionality of z is related to the dimensionality of x, but it's also related to the number of samples that you have. Okay? Any other questions? All right, excellent. So let's move on. Now that we have finally covered all the basics, let's get to a couple of, we're going to spend some time now talking about two of the main topics in machine learning. One is regression, and the other one is classification. Okay? I'm going to talk about regression first, and then we're going to come back to classification. But we are no longer going to be talking about classification using probabilistic approaches, but rather other types of approaches. They're typically called, this is very confusing. In classification, there are two main types of approaches that you can use. One is the generative approach, or generative models, right? Of which the probabilistic approach is a big one, right? It's the typical generative method. And the other ones are called the classifier or classification approaches or classifier methods. Okay? So in classification, you have generative and classifiers, which is a little weird to have classification within classification. But that's, you also see them called discriminative methods. Okay? And in these discriminative methods, we're not going to try to estimate the underlying distribution of the data. Okay. All right. But before we get there, I want to talk about regression. And we're going to start, as always, with linear regression. Or I should say, well, I should be more accurate. I don't mean linear regression. I mean linear methods in regression. Okay. So let's call these linear methods for regression. All right. So let's start with, or let's go back rather, to our classical linear model that we have been using until now, okay? And our classical model is y of, say, x and w, okay, is equal to w0 plus x1 w1 all the way to xp wp, right? Where we have, as before, w0 is our, what do we call w0? Anyone? The bias, very good. And w1 through wp is our, it's the, this is the, it's a specific vector. What's it called? Or what does it represent? The coefficients of what? Right, but they represent specific thing because this linear regression represents, remember, in linear least squares, this linear regression, right, represents what again here? If it's linear, a line, right? And this line is given by two parameters, the bias and the slope or the normal vector, right? Very good. Of the hyperplane. So we can probably write this more compactly as this. The sum from 1 to p of wj, xi, okay? Now this is really cool. This is what we've been using. This is where we started with to define correlations, to define linear least squares, right? But the problem with this is that I can only represent simples that are on a hyperplane, right? But what would happen if my simples, if I have another set of simples that look like this? That's when we start to talk about nonlinear correlations, remember? And things of that nature. Because, yeah, there's no linear correlation, but obviously this is not random, right? There's obviously some underlying function here, right? There's some f that does represent my data. How are we going to extend this simple linear model to be able to represent nonlinear functions? What we're going to do, going to get rid of this linear model here, and we're just going to change this for some function phi of x. Okay? You could write phi of xi if you want. Doesn't matter. And if phi of x is equal to x, right, or xi, then I have my original linear model, right? Sometimes you will actually see this model here. You see this equation that I have here? I'm going to erase the bias. I'm going to make a 0 here. And then I'll just say that phi of, where is it? Phi of 0, right? Or phi sub 0, let's say, it's equal to 1, right? And if that's the case, I can write phi as a vector, which is, or phi function, better, phi function is equal to phi 0 all the way to p, phi p, okay? And I can do the same for w, right? W is going to be w0 to wp, right? And now I have w times phi, it's equal to this, right? So I can just simplify this by w phi, right? Yep, makes sense? Everyone? Okay, good. So all I need is to be able to represent different functions. I need different phis, right? So how are you going to define the phi? Well, it depends what type of function you want to represent, right? So for example, we can use this phi function, the exponential function of negative x minus mu j square divided by 2 times the variance square, right? That should look familiar. That's the equation of a simple Gaussian, right? A univariate Gaussian. So this is called the Gaussian basis function. Okay. So here, as in the Gaussian, this corresponds to the means, right? And this one corresponds to, anyone? The variance. It's also sometimes called the scale, because it defines a scale here of the function, of these types of functions that I'm defining, right? So either the variance or the scale. Yeah, but you're right. In multimodal Gaussian or big covariance. Let's do probably a couple more. Another one that is very popular in regression is this one here. Phi of j of x, it's equal to f of x minus mu j divided by sigma. Same mu j and sigma, the scale and mean, where now this function, f of a, it's equal to 1 over 1 plus the exponential of negative a. And this function right here, it's a famous function. It's called the logistic sigmoidal function. And let's do one more. Another one that is very famous, it's the 10h, which is given by, say, the 10h of a. It's equal to 2 times fa minus 1, okay? Where f, it's the same function I've defined here. Okay, so what regression allows us to do is what we started doing at the very beginning of this class, which is to find these functions, right? This function here. It allows us to find this function, and this function is the underlying function from which these symbols are drawn, okay? So now instead of thinking about what is the underlying distribution from which my symbols are drawn, right? I'm going to consider the function that generates my samples x, okay? Now, this is in 2D. I have a line here, right? In 3D, if I had 3 dimensions here, then that would be a plane, right? Correct? If I had more Ds, that would be a hyperplane, correct? Okay. Now, here, this is a function, right, in 1D. And in 2D, 3D, 4D, and so on, it's a manifold, right? And we'll get to that when we talk about manifold learning, which is nothing else than finding the underlying manifold that defines our samples, right? So again, I want to make this clear. Instead of now assuming that our samples are drawn from an underlying distribution, and our goal is to estimate that distribution, I want to estimate these functions. Okay. All right. So the next thing is to compute the maximum likelihood estimator of this, as we have done before. We compute the likelihood function, we maximize it, we find the values of the parameters, right, that we have here, the w and other parameters that that function phi might have. Okay, I'll do that next time.